one thing to note here is that we'll be using only positive anchor boxes to contribute the L offset, L1, which is also known as the mean absolute error, MAE, while L2 is also known as the mean squared error, which we have learned, which has been taught by our TAs and Swapnil. So, right. Yeah, so the total loss function would be the summation of these two. So we have to incorporate these two loss functions. I would also, I have another set of loss function as well. So I was thinking, should I skip the explanation for this or?
You can if they're not too complicated to follow along.
Okay, all right. Then, so for each anchor box, the network predicts two things. So one being the LCLS category or class in the form of one hot vector. And so one hot vector is nothing but if it will be 1 if it is the right class, and it will be 0 if it is not corresponding to what the object actually represents. And y offset would be a pair of x and y coordinates, so two pairs, one being the xo min yo min and one will be the xo max yo max, or the offsets in the form of pixel coordinates. So as we showed in the previous slide that offsets were two value calculated from two ends, one is the top left and one is the bottom right. So two pairs. Relative to the anchor box. So for computational convenience, these offsets are generally, all right, I'll not add that. So basically the ground truth offsets are computed using the ground truth offset of the B box relative to the anchor box, and a minor tweak in the, you can move over, wait. Actually, I'm really sorry for this. Just a moment. Right. So ground truth bounding box offsets, given this figure, it is very difficult to normalize this over all the anchor boxes. So as I mentioned in the previous slide, after including all the anchor boxes and the aspect ratios, the number is nearly 8,000. So you need a centralized way of representing it. So SSD does not recommend to directly predict the raw pixel values of y offset. Instead, it uses a normalized offset value. So the ground truth B box and the anchor B box coordinates are first expressed in the centroid dimensions format. So y box is again converted to the centroid dimensions. So ybx, cbx will be the centroid of the anchor box, which we are using for reference, and YB and HB will be the width and height of that particular box. Sorry, Y box is the ground truth. Sorry, I missed that. And Y anchor, again, Y XM in, again, two pairs of X and Y values, one for the top left, one for the bottom right. So this would be again converted into CBX and CBY for simplicity. And then YB and WB and HB again would be the width and height of the anchor box.
So one question about, there are two formulas for YGT. Is that with the understanding that the variance is 1 for each of these?
No, I'll go on to that. Just a minute. So CBX and CBY would be X min, which is the top left, plus X max minus X min by 2. So max and min would just be the extreme values of X of that particular box divided by 2. Just to give the centroid of X value, and similarly centroid of Y would be Y min plus Y max minus Y min by 2, and that is the center of the bounding box. And then WB and HB would just be the subtraction of X max minus X min and Y max minus Y min. So the anchor box also follows the same convention. Then the normalized ground truth offsets are expressed as the first formula which is present. So YGT would be CBX minus CAX upon WA. Similarly for the Y coordinates, and then the log values for log values for width and height. So that being WB upon WA and HB upon HA ka log. But generally the values of the elements of YGT are very small. So YGT is very, very less than 1. So small gradients can make it very difficult for the network training to converge. So to alleviate this problem, each element is divided into estimated standard deviation, is divided by its estimated standard deviation. So the resulting ground truth boxes would be divided by, similarly for the x coordinate, it will be rho x, for y it will be rho y. So just dividing them by the standard deviation, and there's also a recommended value. So instead of calculating these standard deviations, they recommend using rho x and rho y to 0.1, and rho w and rho h are recommended to be used as value to be used is 0.2. So in other words, the expected range of pixel error among x and y axis is close to 10%, negative and positive, while the width and height error is expected to be plus minus 20%. But these values are very arbitrary, and this was what they found while training the SST. You can move over to the previous slide. The last one. No, previous. Right. So L offset is L1 smooth here, which is used. So SST was inspired by fast RCNN, which I'll explain a little after a little while. So smooth L1 loss is used here, and the formula is mentioned. So U here represent the each element in error between the ground truth and the prediction. So U is nothing but the YGT minus Y prediction. So smooth L1 is a more robust method compared to the L1, and it is less sensitive to outliers. So it was recommended that in SST this should be used compared to just the normal L1. Right, and FL is the formula on the right is for focal loss. So as a further improvement to loss functions, RetinaNet recommends that the categorical cross entropy function, which is the YCLS, should be replaced with the focal loss, which is FL. So the difference here is the extra factor of alpha 1 minus pi raised to gamma. So in RetinaNet, the object detection works best with gamma equals 2 and alpha equals 0.5. Right. So the motivation behind the focal loss was that if we examine an image, the majority of the anchor boxes should be classified as the background or the negative anchor boxes, so that we don't end up having too many truth values, right? True positives, so to say. So only a few positive anchor boxes are good candidates to represent the target object, and the major contributors to this cross entropy loss are negative anchor boxes. So the contribution of positive anchor boxes during optimization is very overpowered by this contribution by the negative anchor boxes. And so this phenomenon is also well known by the name class imbalance, where one of few classes dominate the rest. So for additional details, you can refer a paper by Lin and others, which discuss the class imbalance in the context of object detection. So with focal loss, it is assured that early on during optimization, the negative anchors would belong to the background and would not create this class imbalance. I feel that is it for this slide.
Can you just tell what is exactly positive and negative anchor boxes?
So positive anchor box is nothing but, so we are also using confidence values, right? So Joseph, can you move over a few slides back where it was showing the IOU? Right. No, just IOU, yes. So here positive could be considered as A1 and A4, where the IOU value for A1 is 0.32 and for A4 it is 0.3. So technically A0, A2, A3 and A5 have no intersection region. So basically their IOU value would be 0, and this would be considered as negative anchor box. Assuming we have a threshold of 0.3, given that we have two values, positive being 0.32 and 0.3, if we are assuming that we have a threshold value of 0.3, because there would be multiple, if we include aspect ratios as well, there would be multiple anchor boxes qualifying as positive. So to eliminate that, we also use a threshold. So assuming threshold is 0.3 here, both A1 and A4 would qualify as positive anchor boxes. And if we assume that the threshold is 0.31, so only A1 would qualify as a positive anchor box, and A4 would also would qualify as a negative anchor box.
Okay.
And you set this threshold because at some point your anchor boxes are going to get too many, and then you're going to start ignoring.
Reduce the computation cost. Joseph, you can move over to the slide with very complicated loss function.
There's a question in the chat from Fennel. Is the threshold for confidence score or for IOU?
IOU. It could be used for confidence score as well, but we will explore that a bit later.
Just bear in mind the time and the slides that you're on. Again, reminder.
Okay, I'll skip this slide.
No, I mean, you don't have to, but like if you can, then explain the high level idea first, and then you can decide whether or not you want to get into the details.
Actually, the thing is, first, I was just exploring what different types of, like how it all started. So learning about the loss function, how the bounding box is created, because unlike a classification which we did in MNIST dataset, so they had only one image, one class and one instance of that class in one image. So it was pretty easy to figure out what was that using a CNN model. But here the main problem lies in localization of the object, warping it to just input it in the CNN and then figuring out what class it belongs to, and then calculating the confidence score. So while breaking it down to the start, because all the papers which I read were like the major focus was on improving the model for localization, and the rest was just CNNs, minor improvements in CNN. So yeah, I can explain this one, but it may take up time, so I guess we can move on. I really initially what the issue was, we had prepared only very few slides, but then I felt bad that so few slides are there. Then I kept on adding more and more as I read, and then it landed up to too many slides. Right, so this is the SSD model architecture. So it uses so just a basic heads up. So multi-scale single shot object detection is the entire name of SSD. So the network accepts a RGB image and inputs outputs several layers of prediction. So a base or a backbone network extracts the features for the downstream task for classification and the offset predictions. And ResNet 50 was used for this. And then after the backbone network, the object detection task is performed by the rest of the network, which we call SSD head. So the backbone network can be a pre-trained network with frozen weights, like the previously, for example, previously it could be trained on the ImageNet classification or jointly trained with object detection. So if you're using pre-trained based network, we can take advantage of the reusing the previously learned feature extraction filters from a large data set. In addition, it also accelerates the learning as the backbone network parameters are frozen. So only the top layers in the object detection are trained. And yeah, and then I won't, should I go into the detail? Okay. So the backbone network normally implements several rounds of downsampling. So either using strides of 2 or by max pooling. Both of the methods were explained in our class. So dimensions, right, so scaling factor could be W by 16 and H by 16, and the dimensions are exact if both the image and the width are divisible by 16. So exact integer values should be used. For example, if we are having a 640 cross 480 image, the resulting feature mass will have dimensions of 40 cross 30, which is 1200. So the number of anchor boxes with aspect ratio equal to 1 after the base, so number of anchor boxes with the aspect ratio equal to 1, sorry. So if you're just using 1200 with just one aspect ratio, that is equivalent to the number of anchor boxes. If we multiply that by multiple aspect ratios, say for example 5 aspect ratios are used, so then this number would be multiplied by 5. So the value total would be 1200 into 5, right, which is 6000. And then so here we limit to aspect ratios 1, half, and 2. So the amount would be 4800. And then the anchor box is also receptive to the field size of each element in the 40 cross 30 cross n filters feature maps. So n filters is nothing but the number of filters which will be used in the last convolution layer of the backbone network. And for each anchor box, both the class and the offsets are predicted.
So you're saying anchor boxes are tied to the aspect ratio, which means like
yes,
the aspect ratio is measured in terms of anchor boxes, not like in literal distance.
So if you are having one anchor box We also, so just the anchor box represents aspect ratio 1.
Got it. Okay. Got it.
So if you're also incorporating other aspect ratios, then for that particular location, we'll be having, for 5 aspect ratios, we'll be having 5. And the anchor box itself is having one aspect ratio equal to 1.
So that's why you said the number of aspect ratios you want to consider, those many different layouts of anchor boxes will have to be created.
So right. Multiplication would be involved, and then that will increase the computation cost. So the class predictor is made of the convolution layer terminated by an activation layer, that is softmax for categorical cross entropy. And the offset predictor is a separate convolutional layer with linear activation. And I would just skip the more details of this, and Joseph, you could move over to the next slide. Right, so coming to non-maximum suppression. So after training the SST network, there was one more issue that was to be addressed. Now there would be multiple predictions for a given object. So to remove the redundant predictions, non-maximum suppression was used. And there are 2 different types. One is the classic NMS and one is the soft MMS. So basically, I'll just summarize it. So when we choose the best bounding box we choose the best bounding box using these 3 points. So one being we first discard all the cells in this probability of object box being present is less than the given threshold. So in the previous case, if I mentioned 0.3, so all 4 boxes on the corners would be ignored and only the center 2 boxes would be incorporated. The second being to consider all the cells with the highest probability of having the object inside. Again, third point being it takes the bounding boxes which are the highest score and removes all other bounding boxes that have an IOU greater than a certain threshold with each other. So as mentioned by Jay, that it could happen that if we are having one bounding box and then there is another object very close to it, and then we also have another bounding box. So if for one box we're having a prediction more closer to another class compared to one class, so that particular class prediction would be totally discarded, and that particular anchor box would be considered for the second class and not the first one. So that is what that point actually means. You can move over to the next slide. Yeah, there were a couple of different models as well, which is RCNN, SPNet, SPPNet, Fast RCNN, Faster RCNN, and YOLO. I'll just quickly summarize all these in the next slides. You can go on to the next slide. So yeah, so the first is selective search. So there can be various approaches to perform object localization in any object detection procedure. So using sliding filters of different sizes on the image to extract the object from the image can be one approach that we call exhaustive search approach. And as the number of filters or windows will increase, the computation effort will also increase. So selective search algorithm uses exhaustive search, but instead of using it alone, it also works with segmentation of colors which are presented in the image. So more formally, we can say that selective search is a method that separates the objects from the image by providing different colors to the object. And this starts by making many small windows or filters, and then this uses the greedy algorithm to grow the region to incorporate different big areas of the image. So similarity between regions can be calculated by S of AB, where S is a text, which is a sum of 2 things, one being the texture and one being the size. So S texture is nothing but the visual similarity between different regions, and size would be the similarity between the regions overall area wise. So using this algorithm, the model continues to merge all the regions together to improve the size of the regions, and this is a basic representation of the selective search algorithm. Moving on to warping, next slide please. Right, so warping is after selection of the region, the image with the regions goes through a CNN, where the CNN model extracts the objects from the region. Now, most of the CNNs have a fixed size for input. So for RCNN, they basically used AlexNet. So AlexNet size, like the size which could be inputted is of 227 cross 227. So it has to be in a way cropped in that particular manner. cropped. Whatever regions we have warped, it will be cropped or squeezed to fit the right filter size, and then the wrapped input for the CNN will be processed to extract the object of size 4096 dimensions. Move on to the next slide. Yeah, so I was going to go into detail here, but you can just see the examples mentioned in the bottom image, and this is just the true positive warped predictions. Yeah, you can move over to the next slide. So this is just summarizing the entire RCNN1, and I'll just explain it just a bit about the SPP net as well. So one more point, again here in RCNN, we are also using non-maximum suppression. So a term used is greedy in front of, so greedy non-maximum suppression. So again, repeating, for each class independently, we reject a region if it has an IOU overlap with a higher scoring selected region, larger than the current threshold which we have used. And then there are also a few benefits which were mentioned here. So all the CNN parameters are shared across all the categories in RCNN. So the feature vectors computed by the CNN are low dimensional when compared to other common approaches, such as the spatial pyramids with a bag of visual word embeddings. So the result of sharing, such sharing is that the time spent on computing the region proposals and features is very small for all the classes, and only the class specific computations are the dot products between the features and the SVM weights, and then also including the non-maximum suppression. So in practice, all the dot products for an image are batched into a single matrix product. I will skip a little detail here. So basically what in the paper, what they're trying to mention was that this was a very good approach, and then due to this sharing, they reduced the computation time by a lot. So initial model was taking right. So the models before this had a mean average precision value of 16%, whereas this model without any approximations made a MAP value close to 59%. I will come to MAP in just a bit, but cutting it short, it is just better compared to the previous algorithms after incorporating all these features. And then there's also a domain-specific fine-tuning involved. Yes, given that we are using a pre-trained network like the AlexNet, we also have to fine-tune it to our current data set, like we also do for the neural networks in text NLP and that stuff. So to adapt the CNN model to the new task and the new domain, which is the warped windows, they use the SGD, which is the stochastic gradient descent, training the CNN parameters only on the warped regions. And then aside from replacing the CNN's ImageNet specific 1000-way to the 21-way classification. So in this paper, they used 20 classes and plus one for the background class. So in total, 21 layer classification. So and the CNN architecture is unchanged otherwise compared to the ImageNet. And yeah, I feel that is it. We can move on to the next slide. Yeah, and then this is the fast RCNN. Again, it is just an improvement over the RCNN. And then what SPPNet does was it uses a maximum pooling layer to extract the most highlighted color from a pixel matrix, which causes the wrapping of the region of interest below. Yeah, so using the max pooling layer differentiated it from the RCNN. And then as far as fast RCNN is concerned, they used ROI pooling for utilizing a single feature map for all the regions. And this wraps the region of interest into a single layer. And then the ROI pooling layer uses a max pooling to convert all these features. And since the max pooling is also working here, we consider fast RNN as an upgrade to the SPPNet. So instead of generating layers in a pyramid shape, they're using just one layer, and that makes it simpler compared to the SPPNet. You can move over to the next slide. So this is just an image of a fully connected network for classification. and it uses linear regression and softmax. And so the B box is further refined with the linear regression. And as mentioned before, fast CNN, as the name suggests, is much faster than SVPNet. You can move over to the next slide. Yeah, this is just faster CNN. I wouldn't waste my time again here. You can move over to the next slide. Yeah, coming to spatial transformers. So right now, the things which we discussed right now, what do you say, were not that aligned to object detection. So as the object should be rotated, which was initially mentioned. So one model which was introduced by Google DeepMind researchers was this back in 2015, named as spatial transformers. So just a moment, I'm just recalling. Right. So in the previous CNN-based models, which we just saw, they were able to achieve state-of-the-art results in classification, localization, just common stuff like action recognition, semantic segmentation. But a desirable property of this system is to be able to reason about the images, is to disentangle the object. Wait. Sorry. So the introduction of local max pooling layers in the previous algorithms, which is the fast RCNN again in SPPNet and the faster RCNN as well. So using that has helped to satisfy the property that object poses should be disentangled, and the deformation should be part deformation should happen based on the texture and the shape. So by allowing the network to be somewhat spatially invariant to the position of features would really help. However, due to typically small spatial support for max pooling, which is 2 x 2 pixels, the spatial invariance is only realized over a deep hierarchy of max pooling convolutions. And immediate feature maps that is the CNN activations in a CNN are not actually invariant to the large transformations to the input data. And this is a very big limitations of CNN, and this is due to having a very limited predefined pooling system for dealing with variations in the spatial arrangement of data. So what they proposed in the spatial transformer was that a spatial transformer, which when included into a standard neural network architecture, it will provide very good spatial transformation capabilities and enhance the prediction values and also the overall accuracy. So the action of spatial transformer is conditioned on individual data samples with appropriate behavior learned during training for the task without extra supervision. So unlike pooling layers where receptor fields were fixed and local, the spatial transformers induced a dynamic mechanism that can actively spatially transform an image or a feature map by producing appropriate transformation for each input sample. So like in the image A, we can see that just a basic MNIST dataset which is deformed. We have 3 different samples here. For the first one, the input is just distorted with random translation being the scale, rotation, and clutter. The second one, it is just rotated by a bit, and the third one, we have a clutter where a part of some other class instances are also involved in that. So yes, so basically, yeah, you can move over to the next slide. Right. So idea of spatial transformers is it would be good to take an input where the images could be as an RGB image, or it could be a layer inside your convolutions, and the output could be a tensor, and it would be good to take an image or that tensor to push it through the network, which would be fully connected to take some parameters, and then these parameters could be the transformation that you want to do on your image. So your parameterizing actually Yeah, so basically the parameterizing what we are doing is involving the theta here. So this is nothing but the affine transformation, affine whatever. So we want to incorporate translation, scaling, and rotation for this localization net. And the way we achieve it is using the affine transformation. So on the left is the original image, and on the right is what we are aiming to achieve. So A theta represents the transformation. The theta 11 and theta 21 represent the scaling factors. Theta 12 and theta 22 represent the first one, theta 11 and theta 21, the first column represents the translation. Second column represents the scale, and the third column represents the rotation. And then, so basically, xt and yt are, what do you say, the pixel values, so the pixel locations on the target, so the v. So for the v figure, xt and yt are just the pixel coordinates, I being just iterated, since we are going to iterate over an entire image. And one question which may arise is how do we exactly know xi and yi of the target image if we just have the input image? So basically the point here was, this is just a pixel location. What we're doing is just mapping the pixel locations to the original data, and we do not actually have the value. So the value being the number, like in black and white image, the values are generally from 0 to 255, ranging on the intensity. So that is what I'm indicating by the term value. And xis, yis is nothing but the actual values of the source image. And then yeah, you can move over to the next slide. Right, so this is how the transformation or the grid is getting parameterized by theta, and gi is basically xit and yit, and it is coming from the target point. And what we're basically doing is we're just mapping these points back into the source. So the objective is to know what the value of the pixel is in the target V image, and we want to read it off from the correct location of the source, which is U in this case. So right now, as the formula which we can see just next to the, so the VIC and the summation formula which we can see on the right of the image, that is the formula used. Now we get the point why XIS and YIS was actually calculated in the first place. Like, why do we want to incorporate the transformations? Why do we want to use the A theta? So we actually need it for this formula. So that is why this was used. And then H being the height and W being the width of the U and V. And mind that U and V would be of same size. And so that won't be a problem here while doing the subtraction and all these things. So what we are actually doing here is bilinear sampling, and basically it is just a bilinear interpolation. So we'll be looking at how we are getting a value for a particular channel, and at a particular location on that channel, at a particular, that is a pixel location on that channel. And what we are doing is just copy pasting from our input, which we get initially from a data set, and what we're doing is summation over U for that particular channel of pixel, and then yeah, and then so basically for a linear interpolation in one dimension, what basically happens is generally we have a line of 0, and then it peaks, and then again it is 0 for most of the value, then there is a small peak in between. So here we call it bilinear sampling or bilinear transformation just because we are using two different parameters. And then just assuming for a case when xi is equal to m, the term would end up being 1, the first term, which is the max of 0, 1 minus xi of s minus m. So assuming xi is 1, xi is m, so that first term will become 1. And assume the yi similarly is equal to n, so again that term will be equal to 1. So then if you're lucky, this generally does not happen for the entire region. But if you're lucky, then these two just turn out to be one, and then what will be doing the summation over, it will just be the u parameters. And then again, for back propagation, we require the partial derivative. So the partial derivative of vi, which is the value of vi, is nothing but the value which we are trying to predict in the v image. So value is nothing but the intensity of the black color. Yeah. So if we are partially derivating it, so partial derivative of vi with respect to u of c n and m, so that term will be equal. So that will reduce to 1, and then since the max terms are independent of u of n comma m, so that will still remain, and hence the summation will still remain. And then if you are partially doing a partial derivation with respect to x of I, it would be same for y of I, similar. So the summation would involve the u of n comma m, and then the maximum of 0 comma 1 minus mod value. And then these are just 3 cases of 3 different values. So yeah, I guess. Yeah, I think you can move. Yes, so right. So in this image, we can see here that yeah, this idea was tested where we used multiple convolutions after doing the spatial transformation. So we did spatial transformation 1, 2, 3, 4 times, and then followed by a convolution. So these are the outputs for multiple single convolution as well as multiple convolution, multiple space transformation used. So if you just focus on the last model evaluation, so there's a single evaluation, single, what do you say, spatial transformation is incorporated. So the the accuracies are 3.7 and 3.9. So sorry, the error values are 3.7 and 3.9, and then the error values for when incorporating multiple spatial transformations, the values reduced to 3.6 from 3.7 for a 64 pixel image, and then the value more or less remains the same for 128 pixels. Now here it is seemingly less, but when we're just summing it over all the different class predictions and all the instances of each class, this would amount to a huge improvement compared to a single convolution network. A spatial transformation, just a single spatial transformation. So again, as we had seen in multi-layer perceptron, after each layer we added non-linear activation. So that so the idea basically was, if we wanted to do multiple transformations all together, so if we are trying to combine all the transformations together, so HT initially, and then inputting it in a CNN, proper CNN, so that would probably fail, because as we had learned that it would it would be boxed into just one spatial transformation because it is a linear one. Now if we introduce nonlinear activations after each spatial transformation, it would obviously be different. So that would be one more way to explore this data set, and I do not have the values for that because that was not done, but this was just a thought which came while looking at these predictions. So classification here which they used was slightly different to what we are actually used to. So basically I feel that they had a data set that could detect over 5 digits. So in the 260 here, they would predict blank, 260, and then a blank. So the different classes would be from 0 to 9 being 10 plus 1 for a blank. So if we had to detect a total of 5 digits from any image, if there is no other digit in that particular image, so if there is less than 5, so it would be replaced with a blank. So that was it. And then another observation here could be that in one particular layer, H and W would remain same, but So let's put it this way. For U and V, for one transformation, the image height and width remain same. But after convolution, the image size shrinks because of all the filters and max pooling and all those things. So, but the U and V size for, again, the second spatial transformation will remain the same. But what we are actually doing is downsampling. So while mapping it backwards, so you need to upsample it first, and then it would during the back propagation, we need to upsample it first and then take it back. And so it's like 1 pixel for the last could end up being more pixels while moving backwards. So I hope that is making sense to you. So what I'm basically trying to say is that due to the convolutions, the image size would shrink, it would downsample, and while back propagation, just to calculate the error values and all those things, we have to upsample it. And that could be done by a couple of ways. We could see the neighboring pixel values, or just 1 pixel could be copied over a range of pixels. So 0 for 1 pixel could represent 16 in the first, while moving up to the first layer. You can move over to the next slide.
Yeah, Jhagrut, just 2 small questions. First is, I must have missed this. What was the motivation of introducing these networks, the spatial transformation?
Right, I was going to come over that. So basically what they said was spatial transformations. Yeah, as mentioned again, what we are looking at was horizontal bounding boxes, and then the aspect ratios were also not incorporating the rotations of different objects. Like this was just the number data set. So here, as you can see, the 9 is rotated, right? So whatever bounding box you use, either the horizontal, it will be horizontal in shape, but whatever aspect ratios we use, the offset value would be very huge. So assume that we are able to capture, while warping, like after warping or whatever, we are able to capture this image upright. So that will improve our accuracies and precision value much more compared to if we're just using the basic prediction method which was defined in earlier slides.
Okay, I got that. And one last question: were there any comments on the algorithmic complexity or the time this algorithm takes to inference, in the paper?
Inference time over what, the entire data set, or
like if I give it one image, let's say an inverted phi, what is the algorithmic complexity of this algorithm? Were there any comments about this on the paper? Is it more complex than the already used cases? Less?
It is less complex for sure.
Okay, got it. Thanks.
Right. Yeah, this was just an extension which I was going to mention. I'm just thinking if I should. So basically what they said was, here we are having just one class object and one instance of that particular class in one image, right? We're taken that we're incorporating all the rotation and everything. It is just one class, and then the noise is also just partial instances of other classes. So the idea was, if we could use multiple parallel layers, like the one which we had seen in the previous slide, multiple layers which would describe or incorporate different features. So here the red one was focusing on the heads, and the green was focusing on the body. So the second image, I don't know the exact name of the bird. So top left, the right to the top left image, the one having the white and slight grayish color. So that is an outlier because the head should have been covered by the red B box, and the green should incorporate the body. So both of them are not actually being predicted correctly. So that is an outlier. And these were just the prediction values which they got on the same data sets, just using 2 different layers. So at the end, you see 2 times HDCNN. So that is nothing but 2 parallel layers of spatial transform, 2 parallel layers, each of them having spatial transformation and CNN. And then for different size, so to 24 pixel and 448 pixels. So, excuse me. So you see the values are increasing if the pixel sizes are more. And then as we are just increasing the number of parallel layers, which may incorporate different types of features. So the accuracy increases here. Yeah, I guess that's it for now. You can move over to the next slide. So performance is a very important metric to compare different data sets, given that we're having multiple data sets, some using horizontal bounding boxes for annotation, some using oriented bounding box for annotation, and some using different transformers and different types of outputs are there, and class imbalance and all these things. If we incorporate all these things, then comparing different models becomes very difficult. So right now there are a plethora of metrics for performance evaluation of object detection algorithms. Average precision, for instance, is a popular metric for evaluating the accuracy of object detectors by estimating the area under curve of precision recall relationship. And depending on the point interpolation used in the plot, the two different AP variants can be defined, and then therefore different results were generated. AP, which is the average precision, also has 6 additional variants, increasing the works, and then increase the workload of benchmarking them properly, and then comparing different models at different approaches to one another. So in the paper titled "A Survey on Performance Metrics for Object Detection Algorithms," they came up with this, they used MAP, which is the mean average precision, as a metric to compare different model evaluation. So considering this image here, so this image has 2 different class instances, one for board, one for person. Move over to the next slide, please. Joseph. Right, so assuming we're just focusing on the board, the A is the anchor box and B is the ground truth box. So these are for a couple of images. So image 1 to 7 is shown here. So I'm just describing this method, how this would be used. Assuming we have a data set of 7 images and we're just predicting one.
About the colors, red and green.
Could you please repeat? I didn't get that.
Do we care about the colors red and green because it's not clear what?
Yes. So green
is ground truth?
Yes, ground truth of board. So in the first image, there are 2 boards, which are represented by the green boxes, one on the top left, one on the bottom right. And then the model predicted 3 different ground, anchor boxes, or B boxes. And then the scores mentioned alongside are the confidence scores representing a board. So just for simplicity, we're just using one, class. So for A, B box, the value is 88% of representing a board. C being 80%, but nothing is there, so this is a wrong prediction. B being a 70%, like the model fees, it has 70%, confidence score. And then similarly for other images as well. So yeah, I guess you get the idea. You can move over to the next slide. Right, so the detections were detections are mentioned here, and we also have the confidence scores in the descending order. So, and then a couple of metrics here have been mentioned: true positive, false positive, accumulated true positive, accumulated false positive, precision, and recall. So we also we wanted to incorporate the confidence values, right? We do not, irrespective of whatever class that particular object is belonging to. Right now, we just using the board, so that is simple. But across classes, it will be difficult to generalize this. So that is why they suggested that we could order the the different confidence scores in the descending order, and then calculate the true positives and false positives. So true positive would be, again, as mentioned in the previous slides, if it is matching the criteria of threshold, like the IOU value or the Jhagrut index is matching the is above, the value of it is above the threshold, so then it is considered as a true positive. And then false positive is nothing but what do you say? So I just forgot what was false positive. Sorry for that. Right. So could you please move over to the previous slide, Joseph? Yeah. So right now, since we are talking about the different ways of calculating how the model is forming, like there are 4 different parameters: false positive, false negative. Like in the classification matrix, what was that? Confusion matrix. There were 4 different values: false positive, false negative, true positive, and true negative. So we have defined what actual true positive is. We also know what true negative is. So true negative is false negative. Wait. What was that? All right, true negative. Yeah, I was going to elaborate on the point of true negative. So anyone could guess what would be the value of true negative here. False positive is just that it should fall into the criteria of threshold. So it should have a greater threshold value of IOU greater than the threshold, then it will be considered as a positive one. So anyone could tell what the value of false negative would be for just one image, given these parameters and all these things, for just one board class.
The A88% in image 1, or like the red with high scores, basically.
So, so true negative would be boundary.
False negative,
Yeah, so true negative would be boundary, and then the boundary could be having pixel size of 1 pixel size, look, 1 cross 1, 2 cross 2, 2 cross 1, 1 cross 2. There could be infinite number of combinations of the boundary regions if you're just focusing on one class. So that way, true negative in this case would be infinite. So basically what we are left with is 3 different parameters: true positive, false positive, and false negative. So true positive, as I mentioned, it should be matching the threshold of with respect to the ground truth bounding box. False positive is an incorrect detection of a non-existent object or a misplaced detection of existing object. So as you can see in image 1, the C is a misplaced value, so it is a false positive. And a false negative would be an undetected ground truth bounding box. So a green image is there, but there is no corresponding a red box for that. I guess there was one example here. Right. So for image 2, you do not have an red box around that which could detect that particular object instance. So that would be considered as a false negative. So basically what we are left with is 3 out of the 4 confusion matrix parameters. So we would have to use metrics which would just involve these 3 values. So the 2 popular ones would be precision. So precision is calculated as true positive upon true positive plus false positive. So basically true positive value divided by all the detections. And then the recall is true positive upon true positive plus false negative. Again, it does not involve true negative. So that is nothing but true positive upon all the ground truth values. So, right, you can move over to the next slide. So coming to the point of confidence scores, and then the reason of arranging it in the descending order of confidences was to calculate to incorporate the confidence while calculating the precision or the model accuracy or whatever, how good the model is. So since we are using the accumulated true positive and accumulated false positive, so we needed to ensure that the accumulated values would be less towards the high confidence scores, and then it would grow on and on as the confidence scores increases. So that was considered as a metric here. So in that way, you're incorporating the confidence score as well. You can move on to the next slide. Right. So this is the actual what do you say, precision recall curve. So precision recall curve can be seen as a trade-off between precision and recall for different confidence values associated to the bounding boxes generated by the detector. So if the confidence of detector is such that its false positive is low, the precision will be high. And in case where many positives may be missed, yielding a high false negative, this would yield a low recall. Conversely, if one accepts more positives, the recall will increase. But the FP may also increase, decreasing the precision. So basically, a good object detector should find all the ground truth objects. The ideal case would be Fn equal to 0. That is very high recall, while identifying only relevant objects as well. So false positive should also be equal to 0 in the ideal case, which is high precision. However, the problem is in practical cases, the precision across recall plot is basically a zigzag line, posing challenges as an accurate measurement of its area under curve. So as we know, generally it is monotonic in nature. So the precision cross recall graph is generally monotonic. So this poses a question that in the region from Y label, which is the second from left, to J, third from left. So if we're subtracting from R to Y, should we add or subtract the value during the region, like in between the region from Y to J? So that was an issue in analysis. Like what about the regions where it is again rising and it is not monotonic in nature? So what they came up with was interpolation. What do you say? Yeah, interpolation only. You can move over to the next slide. So two different interpolations were suggested. One being the 11.1. So starting with 0.0 with the gap of difference of 0.1 until 1. So 0.0, 0.1, 0.2 up till 1. And then whatever point which they're having, they'll interpolate to the left, and that will be considered as the value of that particular location. So as you can see, for point 0, it was the maximum value to the right of it. So that is for point R. So for point 0.1, the maximum value to the right of what do you say, that particular position, which is to the increasing recall. So that would be point J. So that is considered as the value for point 0.1. Similarly, for 0.2, 0.3 values, the value which will be considered would be the point X, which is the peak at 0.4. And then similarly for other points up till G. So that was their idea, to create a monotonic wave. And then you can obviously extend this idea to multiple points so that you could incorporate all the different prediction values of all the anchor boxes, so that you can get an overall view and not just sampled view of whatever, how the model is performing. You can move over to the next slide. Yeah, so this is just incorporating for all the different what do you say, anchor box predictions. Yeah, you can move over to the next slide. And just, yeah, mean is just dividing it by n. So assuming we are just having 11 samples, so it will be divided by 11. So right now we are having A to Y, so 25. So if we are planning to incorporate and interpolate for all these points, n would be equal to 25. Yeah, that's it. You can move over to the next slide. Yes, then all these methods. So basically, for image like a task like object detection in aerial images is very complex, because backgrounds are very complex, and the variant appearances of objects further increase the difficulty of object detection. So what they proposed here was a ROI transformer, which could can you move over to the next slide? I think this one is not that clear. Next slide. Next slide. Yeah, so the basic idea was like we discussed for the simple what do you say, spatial transformers. Sorry. So what they were doing was they were just taking one instance of an object and then they were rotating it upright so that it would be easier for detection. So here, irrespective of however the instances are located, so considering this one type of class which has three different windows when looked from top and that particular creamish color, so all the three instances of this particular class were rotated in a similar manner and upright. So that makes the job of the convolution networks much easier. So this was the basic idea of the paper, and since this was much similar to the spatial transformers, but there's a downside to spatial transformers, which was that could not be used when the number of objects, like number of instances, was very high in a data set. So that was failing in that particular area, and that was not too specific for object detection in aerial images. So that is why they introduced with this idea of ROI transformers, where they could incorporate small and big images alike, rotate it in an upright manner so that all the different class instances look the same, and then the object detection becomes very simple. Yes, yeah, basically that point. Object detection becomes very simple, and otherwise what happens with spatial transformers, what could happen is we may end up with one box incorporating two or more instances, and that is where we do not want to get, because just assume if you want to detect the two buses, any two buses which are very close to each other and aligned in the same manner. So we may have boxes very close to each other incorporating that big particular object instance, and that would involve overcrowding of anchor boxes, and that is why it was failing. So this was a method which they proposed, and then I think if I go into the specifics of this as well, Priyambi would not get time to represent her paper. So I think this was just the end of whatever I had. I was also going to describe the SRDET, which was one more model which was proposed by the same authors. But then keeping the time in mind, I would stop here. I tried my best. Hope you were able to understand. Shrey.
Yeah, I got some of the points. Like it's too heavy for me to absorb, but I took some of the topics in mind and I'll read about them also. So I found your research interesting.
Right. So if you could okay. So the couple of points of feedback, and I'm still recording this because like at some point in the future, if someone wants to review like what feedback people gave to this presentation, we just have it on hand. This was like really well chalked out, really good in the sense of details, like breadth-wise versus depth-wise explanations. And to my understanding, like to create a presentation like this, you have to spend a lot of time know a lot about the area, and like also understand well how to present a certain topic to a new audience. So job well done. That said, there are always like pieces of feedback that you should take that are useful. Couple of technical things, like use a cursor, like share your own slides when you're doing it so that you have a cursor when you're explaining slides with a lot of content so the audience can follow along easily. There are a couple of points, and you are good because like you also pointed out like what section of the slides you're talking about, but it's easier with the red cursor that Google Slides actually gives you. You might be able to break some slides into more decompositions. So like the same final slide, but like build up to it. Use some pictures more than formula. And to be fair, you had those, but just like even more pictures would have been much nicer. But yeah, like it's not like you didn't have pictures, so fair enough. When you have slides like slide 11 I mentioned here, but it was just one of those slides with a lot of math. and you're focusing on explaining it piecewise. And like draw these bounding boxes over the parts that you're explaining and build up to like, okay, this part is what I'm talking about. Here is what I explained. This next part, here is what I'm explaining, so on and so forth. Just like to focus your audience's attention on a certain part of it. There's a lot of information and processing it takes time. So like be aware of your audience. Like this would not have gone well if we had new people on this call, but I am assuming you also would have known that and adapted your presentation otherwise.
Yes.
Be very precise in what you're saying. Don't go back on your sentences. And the caveat is you can always speak more slow, which is something even I'm working on myself. I find it very hard to speak slowly versus just go fast and like go one or two sentences back and update what you were saying. But that doesn't work well for like polished presentations. It would be nice to see a timeline of architectures and like key takeaways from each before you jump into each one. That said, like it was very like you are very good at structure. You explained the problem, introduced the solution, like this model does X differently, and then you spoke about the rest of the model. But it was a lot of information, which is up to people to take away. Make notes for your presentations. Like if you have like a script, the advantage of virtual presentations is you can literally write down a script and stick to it. So that you don't get stuck anywhere at any point in the presentation. I think that's all the feedback I had. If other people have stuff, you can feel free to jump in.
Yeah, I'm sorry I stumbled at a couple of places in between because I'm also having exams, so I also had that in the back of my mind and I was preparing for that as well. So yeah, I'm sorry for that, and it was a lot of information for me as well. So just remembering all the text and all the specific details which were used and incorporated, that was quite a new experience for me and a good one.
No, overall, this would have been like the top 5 or 6 presentations I've seen this year. So pretty good. Cool. If no one has more feedback, then I'll stop recording and we'll switch to Priyamdi.